So today we're going to be extending what we dealt with last class, the moment of inertia, into kind of more applications of how we're actually going to use it. So we're going to introduce this by a little question. Have you ever seen a beam or anything of that nature, rectangular cross section, something like a 2x4, holding up some weight? Is it oriented like that? Or is it oriented like this? And the answer is like that. So any beam is always going to look like that. And the reason for that is because this object oriented in this manner has a larger moment of inertia than this object oriented horizontally. And so that's kind of what the topic of today is, kind of finding the maximum moment of inertia, because the maximum moment of inertia will have the most resistance to rotation or bending. And so that's why you want the biggest moment of inertia whenever you build structures. And so today we're going to deal with actually finding what those moments of inertia are for different orientations of objects, kind of rotating them around. And we're going to do that two ways, mathematically with transformations and kind of graphically using something called Mohr's circle. Before we get into that, there's another item that we need to define, and that is called the product of inertia. So this is similar to what we saw for moments of inertia. Moment of inertia about the y-axis, for example, was x squared dA, but the x-axis was y squared dA. The product of inertia is kind of the combination of the two. So instead of x squared or y squared, it's x times y. So x times y dA integrated over the entire object gives me the product of inertia. And again, we're going to need this to determine the minimum and maximum values. For any symmetric object, so some of the common ones we saw last class, things like spheres and circles, the product of inertia is always 0. So if it's symmetric about either x or y axes, Ixy will be 0. Mainly because you have the same amount of area on each side, and so that's going to cancel out. Physically, Ixy, it's kind of a weird quantity. It doesn't really measure rotation. It's actually more of a measure of the symmetry of the object. So in terms of, if it has a high product of inertia, does that mean it's hard to rotate? Not necessarily. It just means it's highly not symmetric about either axis. Just like in the case of the moments of inertia we saw last class, there's also a parallel axis theorem for the product of inertia. And so if we want to do the product of inertia about different axes that are displaced, so like we had before, I have my x and y axes, I have other x prime, y prime axes, and want to know what the product is around these new axes. Do the same thing I did before, have, if I want to find my new, in this case, product of inertia, I take my old one, the centroidal product of inertia, and then add on the area multiplied by the distance. Before it was the distance squared, so again, perpendicular distance. In this case, because we're dealing with Ixy, the combination of the two, we have the combination of the two distances. So area times dx times dy. So the two distances, we've moved it in the x and y directions. One big difference that makes in this case is previously, it didn't matter whether you moved it left, right, up, or down. Those distances were always squared, and so it always ended up being a positive number. In this case, it could be positive or negative, because if x goes to the right, dx is positive. If x goes to the left, dx is technically negative. Same thing for dy. If it goes up, it's positive, down is negative. So you could end up with some negative values there. So your product of inertia could be less than the centroidal one, which is different than the actual moments of inertia that we saw last class. And so to actually get those rotations, so again, beginning of class, I had a kind of vertical orientation and a horizontal orientation, and that you can get to by just simply rotating your axes 90 degrees. And so instead of sticking to just 90 degrees, we want kind of just general rotations. So instead of translating my axis like we saw before, I want to actually rotate them. So keep them origin at the same spot, but actually rotate these by some angle. So it would go from x to x prime, y to y prime by rotating through some angle. And now I want to find the new moments of inertia, x prime and y prime, about these new axes. And so it's kind of similar definition. Moment of inertia Ix prime will be given by the integral over the y prime axis, y prime squared times dA. And so now I'm looking at this perpendicular y prime distance instead of this perpendicular y distance. But I don't want to do that using those integrals. I want to do it using my old values. So assuming I know the moment of inertia around x and y, as well as the product of inertia Ixy, I can actually get the new ones. So Ix prime is related to Ix, Iy, and Ixy through this somewhat complicated formula. So you have Ix plus Iy divided by 2, kind of the average moments of inertia about the x and y axes. Then you have Ix minus Iy over 2 times cosine of 2 theta, again, theta being the angle of rotation. So whatever this angle is here, that's your theta value. And then subtract Ixy, the product of inertia, times sine of 2 theta. So that's why we needed the product of inertia, so that we can do these transformations and find my new values, Ix prime, Iy prime, and a new product of inertia, Ix prime, y prime, based on the old values, Ix, Iy, and Ixy. If you remember the polar moment of inertia from last class was just Ix plus Iy, that's essentially the rotation about the origin, about the z-axis. Nothing's really changed here. I just rotated my coordinate system, but I still have the same origin. And so I should have the same polar moment of inertia for x prime and y prime that I did for x and y. And it turns out that I do. Same definition, polar moment of inertia, Ix prime plus Iy prime. If you take these two equations and basically add them together, these equations are fairly similar, only difference being that there's different signs there and there, different signs there and there. So essentially those guys cancel out, those guys cancel out, and all you're left with is the average divided by 2, which is just Ix plus Iy. So same value for polar moment of inertia when you rotate your coordinate system. And now the principal moments of inertia, these are really the maximum and minimum values. So when I went back to that, again, question at the very beginning, your beams are oriented vertically because that gives you the maximum moment of inertia. So that's one of the principal moments of inertia. The other one is the minimum, and that's when it's oriented horizontally. And so that is the minimum moment of inertia, but that's also a principal moment of inertia. And these guys will always be offset by 90 degrees. And so vertical maximum, minimum, horizontal, difference of 90 degrees in that rotation. And so you always have two principal moments of inertia, one corresponding to the maximum, one corresponding to the minimum, and they're given at some principal angle. That principal angle you can actually find through this equation. So -2 times the product of inertia divided by Ix minus Iy gives you the tangent of twice the principal angle. Because you're doing a tangent to solve for theta, inverse tangent gives you two answers. So this will have two answers. Those two answers will be separated by 90 degrees, and those then correspond to the maximum and minimum moments of inertia, your two principal moments of inertia. If you want to know what the actual values of those moments of inertia are, you kind of have two options. You can take this value of theta that you find for the principal value and stick it back into these transformation equations, or kind of doing that and solving the equations, you end up with your principal moments of inertia are Ix plus Iy divided by 2, get that average, and then plus or minus. So again, the plus sign will be your maximum value. The minus sign will be your minimum value. Ix minus Iy squared, Ix minus Iy divided by 2, whole thing squared, plus Ixy squared. And then one other thing that happens when you're at a principal moment of inertia, so when you're at a maximum or minimum value, is that the product of inertia, I x prime y prime, will always be 0. So this all might seem a bit weird at this point. So simple example as to what all this means. So let's just assume that we started with some randomly oriented rectangle. I'm going to use a rectangle because we know what the answer should be for a rectangle. And so instead of using the nice horizontal or vertical one that we've seen before, here's one oriented at some weird angle. And let's just say that I know the moment of inertia about the x-axis and the y-axis for this weird orientation. And then now with those given values, I want to be able to find what the principal angle is and what the principal moments of inertia are. So essentially want to find the maximum and minimum values for this orientation. And the answer I'm going to get will actually be the horizontal and vertical ones. So the answers for my principal angles will be for the x prime and y prime axes that make this either vertical or horizontal. So this x prime axis, moment of inertia about that guy will be basically the horizontal orientation. So that'll be the minimum moment of inertia at that angle. The other answer I will get for the principal angle will be either that one or could also be that one depending on how you do your angles. But in either way, that is the moment of inertia about this y prime axis, and that will be in its vertical orientation. So that will be the maximum. So again, principal angle gives me the orientation to kind of reorient this into its orientation that gives me the maximum minimum values, in this case, back to the horizontal or vertical rectangles. So that's the mathematical way to find principal moments of inertia. Again, there's also this graphical way to do it called Moore's circle. And so we need a bit of notation. So we've seen this combination in a lot of the equations, Ix plus Iy divided by 2. That's my average moment of inertia about each axis. I'm going to call that new variable A. And then there's also this combination we kind of saw in those previous equations, Ix minus Iy divided by 2 whole thing squared plus Ixy squared, square root of the whole thing. I'm going to call that capital R. If you haven't guessed already, capital R will be the radius of Moore's circle. So using those definitions, I can basically stick those definitions back into, again, those original long, these guys here, transformation equations. And what I get out of that is a new equation that looks like this. So Ix prime minus A whole thing squared plus Ix prime y prime squared equals capital R squared. Now, if you remember the standard equation of a circle, radius R centered at A comma B, it's x minus A whole thing squared plus y minus B whole thing squared equals R squared. Compare that to the equation we have here. And basically Ix prime will be like our x axis, x variable. A is going to be where the circle is centered along the x-axis. Ix prime y prime will be like our y variable. No offset for the center. So the center of my circle is going to lie on the x or Ix prime axis. And then the radius of my circle is there as well. So basically what I have is a circle centered at A comma 0, radius R in my coordinate system that has axes of Ix prime as my x-axis and Ix prime y prime as my y-axis. So how to actually draw Moore's circle and how to actually use it. So again, this is assuming we know the original coordinates, Ix, Iy, and Ixy. So first thing to do is set up my coordinate system. So I have Ix prime as my x-axis, Ix prime y prime is my y-axis. So it's just standard coordinate system. And then I know I can draw my circle. I know the center point. So find the value of A, the average moments of inertia, Ix plus Iy divided by 2. And whatever that value is, comma 0, is my center of my circle. I can also find the radius using, again, this previous equation here. So use that. I know Ix, Iy, and Ixy. So use that to solve the radius. So now I know the center and radius of my circle, so I can draw that. Once I have my circle drawn, I want to locate a point that corresponds to the original x direction. So I'm going to call this point A. And so that should lie on my circle. The way to find that is to realize that at the x-axis, at that angle theta, my x prime moment of inertia will just be Ix, and my x prime y prime product of inertia will just be Ixy. So my original, that's again my original kind of axis. So that basically tells me where my original axis is on Mohr's circle. So that's going to correspond to theta equals 0 in real life. Then I can do the same thing for the y direction. So for the y-axis, usually call that point B. That is Iy. So again, that's where my new rotation Ix prime lines up with Iy. That's going to be at a y value on my Mohr circle diagram of negative Ixy, the original product of inertia. And that's going to give me theta equals 90. So again, if I have my coordinate system, Ix, Iy, then x prime and y prime that are rotating. Once x prime rotates through 90 degrees, it's at Iy. So that's why Iy is my x coordinate, because x, again, corresponds to Ix prime. And then once you have that all nice and drawn, to find the principal moments of inertia, it's fairly easy. That's just where the circle intersects the Ix prime axis or the x-axis. Want to find the principal angle, that's just half the distance from point A to the x-axis. So wherever point A is, that's going to make an angle with the x-axis. That's going to be twice the actual principal angle. So one thing about Mohr's circle is that every angle on Mohr's circle corresponds to twice the angle in real life. So when we draw point A and point B, they're actually going to be on complete opposite sides of the circle, so 180 degrees apart, which again corresponds to half of that in real life, so it corresponds to 90 degrees in real life. So this is a lot to digest in words. In pictures, here's what Mohr's circle is going to look like. So I have, again, first step, I draw my Ix prime, y prime axes, so two axes, and then I can locate my center point. So that's at some distance, I average, so A, same thing as I average, that's where my center is located, right on the x prime axis, so 0 in the y direction. And then I know my radius, so from there I can draw my circle around the center point. And then to find point A, I just plot a point that's whatever my original Ix prime moment of inertia about the x-axis is, that's my x value, x coordinate for point A. Whatever the original product of inertia value is, that's my y value, again for this point A. And it should lie in the circle if you did everything right. So there's point A. As I said, point B is 180 degrees away, exact opposite point. That should correspond to my original Iy value and negative Ixy. And then as I said, that's going to make some angle with the x-axis. That's twice the actual principal angle. So whatever this angle is, I can find my principal angle. And then if you want to find your maximum and minimal moments of inertia, there's your maximum moment of inertia. Whatever this x value is Imax. Minimum moment of inertia, whatever that value is Imin. So there are your two principal moments of inertia. There's your principal angle, and basically all found through geometry / trigonometry. So equations of a circle, sine theta, cosine theta, center point offsets. So basically all found through geometry at that point. So that's another way to find principal moments of inertia using Mohr's circle. So that was all for the geometric moment of inertia. And as you'll kind of see, the geometric moment of inertia is really good for prevention of bending. So again, when I talked about those beams, the axis that you're rotating around is actually an axis that is kind of in the plane. So my axis kind of goes through here. So that's my moment of inertia about the x-axis. The actual rotation about that plane kind of means it comes in and out of the page. So if I was to look at this kind of from the side, I would have this beam and it's rotating about some axis down the middle. So my axis comes in and out of the page here. So basically what that makes it do is kind of bend. And so that moment of inertia we just talked about, the geometric one, is very useful in beam design. And that's something that will be very useful in one of your next classes, CEE 220, Mechanics of Materials. There's another way this class goes. So this class is a big prerequisite to that class. It's also a big prerequisite to dynamics class. And so when dealing with dynamics class, the moment of inertia that we deal with is called the mass moment of inertia. They may just call it moment of inertia, so unfortunately has relatively the same name. But this is the one that is actually how hard is it to rotate something. So the rotation of the previous one is kind of this weird kind of bending rotation. This one is the actual, I have an axis, how hard is it to actually spin this thing around as opposed to bend it around. So again, the previous ones are purely geometric, only depend on the cross-sectional shape, essentially, which is why it was primarily a 2D thing. The mass moment of inertia will depend not only on the shape, but also the mass distribution. And so this is more of a 3D quantity, usually. And so similar definition, my moment of inertia, mass moment of inertia, is integral of r squared dm. Again, previously it was either dA or dV, but now we have this mass associated with it as well. Again, r being the perpendicular distance to some little elemental mass dm. If I have a constant density, again, I can replace my mass with density times volume, and if density is constant, I can pull it out. So I'm just left with r squared dV. And then that will be a purely geometric construct. But again, this is the three-dimensional geometrical construct as opposed to the previous two-dimensional version. But this is very similar to everything we've done before. There's a parallel axis theorem for the mass moment of inertia, exactly the same as the one we had before. A new mass moment of inertia is the old centroidal, but in this case, instead of centroidal, it's center of mass, because again, it's not centroid geometric, it's center of mass. And then again, instead of area, I have mass, because that's what I need there. And then again, d squared, so distance squared that I move my axis. So everything, again, very analogous to what we've seen before. I can have a radius of gyration, again, very similar, but instead of area, it's mass. So I equals mass times k squared, k being the radius of gyration. And then again, like we've seen before, these mass moments of inertia, if you have a composite body, so something that's made up of smaller shapes, you can take the moments of inertia of each small shape and add them all up, provided they're all about that same axis. And if they're not about the same axis, you can use the parallel axis theorem, again, like we did last class for the geometric moments of inertia. So everything, again, here completely analogous to the previous moment of inertia situation. And so for these composite bodies, so again, simple shapes, things like rods, square plates, rectangular prisms, discs, cylinders, cones, spheres. There's your moments of inertia about each axis. And again, these are about the center of mass. These are assuming that, again, these are homogeneous objects. And so the moments of inertia about the centers are all given there. If you want to move the axis, it's parallel axis theorem with those values. If you want to add them together, again, similar to what we did last class. So that is the principal moments of inertia, minimum, maximum values, as well as the mass moment of inertia. And so that concludes our talk about moment of inertia, other than the examples we'll see later on in class.